I am Professor Devendra Singh, taking this course on machine design, and till now we have covered the design against static load, and this is our design against dynamic load part 2. We have discussed about the various types of the fluctuating stresses, and we have discussed about the fatigue failure. So, this lecture will be including the fatigue and fatigue failure. Then we will discuss the ascent diagram and endurance limit. Then we will move to the next important topic and important knowledge we will try to gather from modifying factors to endurance limit, and then infinite life problem, finite life problem, Soderbergh criteria, Goodman criteria, and so on. So, recap our last lecture, fatigue and fatigue failure. Fatigue is the incapability of a material to take further load. किसी भी मटेरियल में अगर आगे कार्य करने की या लोड लेने की क्षमता नहीं होती है तो उसे बोलते हैं मटेरियल इज अंडर फैटिग. एंड फैटिग फेलियर, if a material is subjected to the fluctuating stresses, the material fails even below the ultimate tensile strength, and if the material is subjected to completely reversible stresses, if material is subjected to completely reversible stresses that we have discussed in the last lecture, completely reversible, then in more than 90% cases, failure takes place below the yield point. Below the yield point, failure takes place. So, this is fatigue failure, and fatigue failure is a most critical situation in mechanical engineering, as most of the systems involves in the motion and the force. So, fatigue failure may take place, and fatigue failure, the characteristic of fatigue failure, it takes place without any warning. This makes it very dangerous. ये बिना किसी वार्निंग के आता है, without any warning, right, and it will be a physical fracture. That is fatigue failure. This is the characteristic. As far as the mechanism is concerned, for the fatigue failure takes place in two steps. First step, as far as the mechanism is concerned, first is the initiation of a crack. And in second stage is the propagation of crack. As we all know, the stress is F upon A. If area reduces, then the stress increases. So, if there is any crack, the effective area which will offer the resistance against the externally applied load, अगर कहीं पे क्रैक होगा तो हमारे मटेरियल में जो इफेक्टिव एरिया होगा, जो रेजिस्टेंस ऑफर करेगा, वो एरिया की वैल्यू घट जाएगी, जबकि लोड, this is our application requirement, load will remain same. If A goes down, then the value of this fraction will goes up, that is stress. And if this crack is propagated further, so this area will continuously goes down and the effect will be continuously increasing in the in this stress, and somewhere this stress exceeds the strength of the material, and it may take place inside the material, and this crack may be the scratch caused by the machining. It may be on the surface, it may be the material defects and in their discontinuities, where this crack will be considered as the initiation point, and further it will be propagated. And it is very good example I have given in the last lecture, that is, if we bend a wire equally in to opposite direction without any equipment, without any scissor, chisel, we can break the wire into pieces. Last lecture में ये मैंने एक एग्जांपल दिया था. So completely reversible, स्ट्रेस लगाई, बराबर एक तरफ को घुमाया इसको वायर को, फिर दूसरी तरफ को घुमा दिया. तो ये जो फाइबर है, लोअर मोस्ट फाइबर एंड द अपर मोस्ट फाइबर, इनको अगर मैं देखूं, दोनों को एनालाइज करूं, तो पहले केस में जो ऊपर वाला फाइबर है वो कंप्रेशन में है, दूसरे वाले केस में ये अंदर वाला फाइबर ऊपर आ जाता है, तो ये टेंशन में कंप्लीटली रिवर्सिबल स्ट्रेस इफ द एंगल ऑफ बैंड इज सेम, then this is the situation of completely reversible stress. So, without any heating, without any chisel, without any equipment, you just find after few bands it will break into pieces. This is a fatigue failure, right. So, fatigue failure is always a very dangerous state. We should consider it very seriously, and the design, that is why we understand or we take this topic separately, design against dynamic load. So, against static load, when we design, we consider the true strength, that is the yield point in tension and ultimate tensile strength. These are the failure stresses or the strength of the material, and if we want to include some reserve strength, then we have introduced the factor of safety. Here also factor of safety remains same, but for designing the components against the dynamic load, a new strength will come into the picture, and that is called the endurance limit. And to determine the endurance limit, we have to plot the SN diagram, and it is tedious, time taking and costly exercise to plot a SN diagram and to determine the endurance limit. So, in a designer use the data available to get the endurance limit, or the relation that we have obtained in our literature between the endurance limit and the ultimate tensile strength of the material, because ultimate tensile strength we can determine by a single test performed on the universal testing machine. Whereas SN diagram हमें समझ में आएगा कि SN diagram ड्रॉ करना कितना टाइम कंज्यूमिंग है, कॉस्टली है, मटेरियल वेस्टेज है, वो क्या है. सो एंड्योरेंस लिमिट ड्रॉ निकालने के लिए SN डायग्राम प्लॉट करना होता है. SN डायग्राम प्लॉट करने के लिए वी हैव टू परफॉर्म द हाई स्पीड रोटेटिंग beam test done by R. Murray, and the specimen was a simple specimen like this. This is a specimen used by R. Murray in his high speed bending test. It is subjected to this bending load W. The length of this specimen is 85 mm, standard length, and the radius of curvature is 250 mm, and the minimum diameter is 7.5 mm, and it is having the mirror polished. Why it is mirror polished? When we discuss about our modifying factors, it will be clear why mirror polished. In longitudinal direction, why in the longitudinal direction, that will be clear later. Longitudinal direction, mirror polished specimen we use, and how we will rotate this with the help of some motor, some counter here, we can a counter, this is the rotating device, motor you can rotate, and we just observe here it break into pieces. So, first step, we apply this load equal to the ultimate tensile strength, and as soon as ultimate tensile strength or more than ultimate tensile strength, the material will not complete a revolution, it will break into two pieces. So, now we draw all the experimental data. Similarly, we increase this value of W की वैल्यू धीरे धीरे बढ़ाते हैं और हम ये काउंट करते हैं कि कितने रिवोल्यूशन इसने कंप्लीट किए. यहाँ ट्रांसवर्स लोड लगाया है तो बेंडिंग इस सिचुएशन है. दिस इज द सिचुएशन ऑफ कंप्लीटली रिवर्सिबल स्ट्रेस. दिस इज द सिचुएशन ऑफ कंप्लीटली रिवर्सिबल स्ट्रेस. सो वी गेट ए नंबर ऑफ डाटा. हर बार एक स्पेसिमेन टूटेगा. हर बार एक स्पेसिमेन टूटेगा मीन्स वेस्टेज ऑफ टाइम, वेस्टेज ऑफ मटेरियल. उतना मटेरियल हमारा खत्म हुआ, उसे यूज़ नहीं कर सकते. अगली बार उस स्पेसिमेन, अगला पॉइंट लेना है तो नया स्पेसिमेन इस्तेमाल करना है. अब W हम धीरे 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 घटाते रहेंगे. जैसे जैसे W घटाएंगे SU2 से नीचे की तरफ, वैसे वैसे नंबर ऑफ रोटेशन, लाइफ टूटने से पहले नंबर ऑफ रोटेशन बढ़ेंगे. अब नंबर ऑफ रोटेशन बढ़ने तो यू कैन अप्रिशिएट इफ द मोटर स्पीड is 14, 40, 2000, 3000 RPM and it will break after 30,000. So, एक पीस को टूटने के लिए, एक डाटा मिलने के लिए 10 minutes. And similarly, it may go up to the 10 to power 6. When we go into detail further, we decide the endurance limit when this specimen will complete at least 10 to power 6 revolutions. 10 to power 6 revolution 3000 की स्पीड पे 3000 RPM हो, एक मिनट में 3000 RPM रिवोल्यूशन कंप्लीट होता है. तो 10 टू पावर 6 रिवोल्यूशन कितनी देर में कंप्लीट होगा, तो 10 लाख को 3000 से डिवाइड करके देखें, यू विल गेट द मिनट्स एंड देन कन्वर्ट. एक डाटा पॉइंट आने के लिए कितना समय लगेगा, यू कैन अप्रिशिएट इट इजीली. सो इट इज़ टाइम कंज्यूमिंग एंड द मटेरियल लॉस इज देयर. That's why we use the data available, designers use the data available for various materials. Even we use the relationship between the endurance limit and the ultimate tensile strength to determine the endurance limit of any material. So, now we start to discuss about the SN diagram. So, SN diagram, if we plot the data on simple log-log curve, even for the ferrous materials, we do not get the knee point. This is something like this, and this does not serve our purpose. But if the same data, if the same experimental points we plot on the log-log curve, then we get a knee point, and that defines the endurance limit. That is our requirement. So, here we need to point, we need to draw this on log-log curve. So, for log-log curve, on ordinate axis we plot log SF base 10. On abscissa we plot log number of revolution base 10. So, this is origin, this is origin. If this W is equals to, if this W is equals to SUT. So, ideally I will get there is no revolution complete, and this is the point, and this is the point, this is the point. This point is log SUT base 10 on ordinate. This is a failure point. Then we further reduce this W below SUT. So, we will get another point. हम गए इसको log, हम इसके नीचे गए 90% तक. This is 90%, this is 90% of 0.9 SUT. This is ultimate tensile strength. We get a corresponding number of revolution 10 to power 3. That is why on abscissa this is 3, and there is a linear drop. So, we draw this line like this, then we reduce further we reduce and we go up to somewhere between 6 to 7, यानी 10 to power 6 to 10 to power 7 revolution. Then we get this is linear portion here, and after 10 to power 6 this lies this point lies somewhere between 10 to power 6 to 10 to power 7, but for numerical purpose and for make our design and recommendation safe, we consider it is at 10 to power 6. Then further it will become parallel to abscissa axis and knee point we have obtained. We have obtained a knee point here. We have obtained a knee point here, and this is an horizontal line, and this point we define this is log S, this is log S E prime. S E prime is the endurance limit of the specimen, and this is defined the maximum completely reversible stress. You can define the endurance limit, that is a maximum completely reversible stress which can be induced in the material without any failure for infinite life. The life of the component beyond 10 to power 6 will be considered as the infinite life. 10 to power 7 के आगे हम कहते हैं वो infinite life है, and this point we should give the name A, we should give the name, this is point A, this is point B, C. So, C के नीचे जो स्ट्रेस लेवल है अगर वो इंड्यूस करते हैं तो सर्वाइवल इसका 10 टू पावर 7 साइकिल से ज़्यादा, और दैट इज कॉल्ड द इनफाइनाइट लाइफ. तो पॉइंट सी विल in fact lie in between 10 to power 6 to 10 to power 7, 10 की घात 6 10 की घात 7 के बीच में कहीं ये पॉइंट होता है, but for our numerical purpose we consider it is at 10 to power 6, that's why this is 6. So, this is endurance limit. This is our ascent diagram. So, ascent diagram I have defined this endurance limit. What is endurance limit? Now, endurance limit, endurance strength same. One more term is the fatigue strength. Fatigue strength is defined corresponding to life, finite life. अगर ये हमारा कोई नंबर ऑफ साइकिल हैं n, ये एक पॉइंट है, ये पॉइंट D, दिस इज ए फेलियर पॉइंट. इसके कॉरस्पॉन्डिंग जो मटेरियल की स्ट्रेंथ है that is called fatigue strength, SF. SF endurance limit and endurance strength. In fact, I prefer to use endurance limit as the perfect meaning for infinite life. अगर उससे नीचे की stress level है तो endurance limit है. Endurance strength, some authors use endurance strength also, but fatigue strength I define corresponding to some life of the material. कि इतना इससे इतना मैक्सिमम इतना स्ट्रेस लेवल इंड्यूस करें कंप्लीट रिवर्सिबल स्ट्रेस में, सो इट विल कंप्लीट finite life. Finite life means if the life of the component is less than 10 to power 7. So, ascent diagram we have covered, we have discussed what is the endurance limit. So, one more time I write what endurance limit. The endurance limit you can think, you can write the maximum completely reversible, completely reversible stress reversible stress that can be that can be induced in a material for the survival of the material for more than 10 to power 7 reversals, that is your endurance limit, that is called the endurance limit, that is called the endurance limit. Fatigue strength, the maximum completely reversible stress that can be induced in the material for a particular number of reversals. Now, the modifying factors that is S prime E in the last, this S prime E. S prime E is the endurance limit of a specimen. So, this is determined in controlled atmosphere, that is the value of the lab experiment. So, in real time we have to use some modified strength, because there are a number of factors which can affect the strength of material, and the strength may get reduced. So, we have to modify the strength endurance limit to use it in our design to make our design as a safe condition and to face the unprecedented situation also. So, the modifying factors, there are a number of modifying factors, but for academic purpose we will discuss about the surface finish factor. What is the surface finish factor? Then we will get we will discuss about the size factor, the next is size factor, and then we will discuss about the reliability factor, then we will discuss about the temperature factor, then we will discuss about the next is the stress concentration effect and the stress concentration factor Kf. This is very important. So, in fact, surface finish factor, the scratches can be treated as a crack, and if crack is initiated due to the machining, due to the erroneous or the low grade finishing, that may cause to fatigue failure. So, we will consider some surface finish factor to modify our endurance strength. Then we use this size factor. So, if every material is having some defects, so those defects in the crystal structure may perform or may act like a crack. So, if the size is more, then the probability of any dislocation, any imperfection may initiate or may work like a crack, and then further it will propagate. Those chances of failure may be increased. So, to compensate, to incorporate this effect and to avoid the failure due to this dimension, we use the size factor to modify the endurance limit. Then the reliability factor, everybody likes to purchase and to have the equipment. हर आदमी चाहता है कि जो कुछ वो खरीदता है मार्केट से वो एक लाइफ साइकिल कंप्लीट करे, एक डिज़ायरेबल लाइफ, डिज़ायरेबल effectiveness, desirable efficacy or efficiency के साथ complete करे, that is called the reliability. So, if we want to get the better reliability, then we have to modify the strength. So, what reliability is desired for particular component, some factors we use to modify the adherence limit in our design. Then the temperature factor, we are aware about the thermal effects in the on the strength. So, we use this temperature factor to bear or to fight against the thermal effects. And then finally, there are number of the application in mechanical engineering, where we need to make the components with the abrupt change in the cross section. We need to provide some holes. So, we need to some arrangements for assembly purpose. So, the area abruptly change at particular section. So, that invites the high level of the stresses, that is called the stress concentration effect. And to incorporate this in our design against dynamic load, so stress concentration factor will be included in our design. So, all these factors in detail we will discuss in the next lecture. So, for this lecture, this is from my side, and we will meet again in the next lecture to continue with the design against dynamic load. With modifying factors of endurance limit, we will start again. Thank you very much.